Okay, for inviting me to give me the opportunity to share this work with you. And this is a joint work with Yongyu here in the Chinese University of Hong Kong. Okay, so let me first show you the equation. The Poisson-Boltzmann model is a model to describe the ion concentration in ionic solution with a charged surface. And it's like this is an elliptic equation with non-exponential nonlinearity and some non-local coefficient. And the exponential function here comes from the Boltzmann distribution satisfied by the ion concentration. So it's called the Poisson-Boltzmann model. And the non-local coefficient, the integrals of e to the u and e to the minus u, indeed, it comes from the condition of charge conservation. So we call it the charge conserving Poisson-Boltzmann equation. And in this problem, we want to consider the possible singularity point, that is a fixed point charge in this system. So we puncture the domain omega at some location P1, P2 to Pn to involve the possible singularity. Okay, so now I'd like to introduce some physical background of this problem. The Poisson-Boltzmann equation can be dated back to the early 20th century from Goldschapin theory. And this is about the electric double layer. So what is the electric double layer? If we consider a container with ionic solution inside, and we put an applied voltage on the boundary, then the ions will be attracted to or repulsed from the boundary, depending on its sign. Okay, and so we have a region of higher concentration of ions and form a layer. Such a phenomenon was observed, and the models were proposed very early from Helmholtz in 1853. He proposed the first model about the ion layer. Okay, he considered that there will be some ions absorbed firmly to the boundary, and the number of the ions is linear dependent on the voltage applied. And later, Goyet and Chapman and the independent Debye Hugo proposed another model, which is a diffuse model. That is, they think that the ions in the region has higher concentration, but they are still free, they are diffused in the water. And the ion concentration decreases exponentially from the surface to the bulk. And later, Stern further modified the Goldschapin model. Indeed, Stern's model combined the Helmholtz model and the Goldschapin model. That is, in his model, there will be a first layer that, as in the Helmholtz model, that ions were absorbed firmly on the surface, and this layer is called the Stern layer nowadays. And next to Stern layer, there are still some diffuse ions at higher concentration here, and this is called the diffuse layer or Debye layer. Okay, so Poisson-Boltzmann equation indeed comes from the Goldschapin model, Goldschapin theory to describe the diffuse part of this the ionic solution. So in particular, we can use a boundary layer solution to the Poisson-Boltzmann model to describe the Debye layer of the ionic solution. Okay. Okay, now I'd like to show you how to derive the Poisson-Boltzmann equation from the Goldschapin theory. We can start from the Gauss law, that is the divergence of the electric field, which is proportional to the charge density. And on one hand, the charge and the electric field can be written as a gradient of electric potential with a minus sign. On the other hand, the charge density rho is nothing but the charge density of the positive ions minus the charge density of negative ions. So we can combine these three identities together to get this Poisson equation, which states the relation between the electric potential and the charge density. Okay, and in Gold-Chapman theory, they predict that the ions will satisfy the Boltzmann distribution. That is, for negative ion Cn, it equals e to the u times some constant. And for Cp, it equals e to the minus u times another constant. So how to determine these two constants? So imagine that we now have a container with ionic solution inside. So the ions will not flow in or flow out of the container. So we can consider that the total number of the ions are conserved or the charge are conserved. So we can count the total number of the negative ions, that is, take the integral of Cn equals the total number alpha, and the integral of Cp will equal some constant beta, the total number of positive charge. And if we take the Boltzmann distribution inside the integral, then we can solve these two constants. Cn0 equals alpha over the integral of e to the u, and the Cp0 equals beta over the integral of e to the minus u. Okay, and the last thing here is in our Poisson equation, there is a constant, this variant epsilon, which is a physical constant, and is called the dielectric constant depending only on the medium. In the case of ionic solution, the medium is water, and basically it can be regarded as a very small coefficient. Okay, just like this. So it allows us to study the asymptotic behavior of the solution to this model as epsilon goes to 0. Okay, so the previous derivation gives us this charge conserving Poisson-Boltzmann equation. As I mentioned earlier, the alpha and beta are the total charge of negative and positive ions. And for the boundary condition, U0 is the surface potential. And here we write the dielectric constant as epsilon squared.
X1 in the metric space X.
Excuse me? Well, I didn't hear the question.
Yes, maybe some random noise, so you can go ahead.
Okay. Okay, so we just write the dielectric constant as epsilon squared to coincide the order of the differentiation. Okay, for some notation simplicity. Okay, so the Poisson-Boltzmann equation comes from the Gold-Chapman theory, can be regarded as a description of the stationary state of the ionic solution with charge surface. And if we consider the time evolution from the middle of 20th century, the Poisson-Planck theory was developed to describe the transport of charged particles. And since then, it is applied to many fields like the semiconductors, ion channels, batteries, and so on. And this equation consists of the Nernst-Planck equation of the ion concentrations, and for the electric potential is the same. We have the Poisson equation between the electric potential and the charge density. Okay, and if we consider the stationary state solution of the Poisson-Planck equation, we can solve the flux on the right-hand side of the equation of Cn and Cp to get Cn will equal to some e to the u times some constant, and the Cp equals e to the minus u times another constant. So it is indeed the same as the Poisson-Boltzmann equation. So that's to say that the Poisson-Planck theory coincide the Poisson-Boltzmann theory in the steady state. Okay, so for the time evolution problem, Poisson-Planck equation, the well-Poissonist long-time behaviors was studied by Byler, Herbst, Najeya, by the Dobu and also myself and Taisha and the other people. And as I introduced earlier that we want to consider the possible fixed point charge in this system, we can also consider possible fixed point charge in the Poisson-Nernst equation. In this case, the problem was studied by Byler and Najera, and they considered a simpler case with only one species of ions and one fixed point charge. And recently, myself and Yongyu studied this problem in a more general setting with two species ion and multiple fixed point charge. Okay, let's come back to the Poisson-Boltzmann equation. And now we want to add some fixed point charge in this system. A related problem was studied by Rubinstein, Friedman, Tintarev, and Kreiwich, Najera, and some other people in 80s and 90s. And they considered the radius matrix solution on annuli. And this situation can be considered as inside the annulus domain. It can be regarded a charge hole inside. Okay, so not mentioned in their paper, but if you choose suitable boundary condition in the inner boundary and take the inner radius to 0, then their solution indeed converge to some solution to the Poisson-Boltzmann model with a Dirac measure centered at the origin. And in particular, the Dirac measures are usually used to describe point charge. So we can consider such a problem that the Poisson-Boltzmann model with some Dirac measure on the right-hand side being the fixed point charge. But we want to consider a more general case that maybe the singularity can not just described by Dirac measure, it can be delta or delta square or something else. So we just puncture the domain at some location P1 to Pn to involve all possibility of the singularity. Of course, we want to figure out what kind of singularity can the solution of Poisson-Boltzmann model have later. Okay. So let me introduce some known results of the charge conserving Poisson-Boltzmann equation without singularity. So we consider this equation in the whole domain omega. The existence and uniqueness was proved by Junzhang Li in 2014. It's based on a variational principle by direct method. Okay. As for the asymptotic behavior, we focus on the case alpha equals beta, that is the total electroneutrality. But the assumption is natural because if we just have a container with ionic solution inside, then it automatically is electroneutral on the total range. Okay, so under the electroneutrality, in 2016 proved that given any complex subset K of omega, then the difference of U at any 2 points S1 and S2 on K will goes to 0 exponentially as epsilon tends to 0. So this result gave us that the solution will become a very flat profile in the interior of omega as epsilon small. Okay, if we now consider a one-dimensional case that is n equals 1, then omega is nothing but an interval from A to B, then the situation is more clear that Li and his collaborators prove that indeed in the interior point, the solution U will converge to some constant. That is, the constant is the average of the boundary condition. Okay, so now we want to ask some questions. The first one is for the dimension n is greater than or equal to 2. We only know that the solution becomes a flat profile. Can there be a limit for the solution as epsilon go to 0, as in the one-dimensional case? Of course, This result only gives us that it becomes flat, but it cannot prevent the possible oscillation. So it's the question we want to answer. The main difficulty comes from that the equation of Poisson-Boltzmann equation is indeed invariant on the adding a constant. That is, if you put u plus c for some constant c into the equation, and on the left-hand side, the constant take Laplacian equals 0, and on the right-hand side, here give you e to the c, and also e to the c on the denominator, they cancel out. And the second term, you will have e to the minus c here, e to the minus c here, also cancel out. So it is invariant on the adding constant. And therefore, if there is a constant exists, the limit exists, the constant cannot be a priori determined by this equation. Okay, and the second question is, if we consider the possible fixed point charge in this system, can we still have existent uniqueness? And if it exists, what's the asymptotic behavior as epsilon goes to 0? Okay, so for the existent and uniqueness part, the main difference is that the solution might not be an echelon function. So even if it has some variation structure, we have to modify the argument to apply for this equation. And in order to analyze the asymptotic behavior with a fixed point charge, I have to point out that for this case, no maximum principle is satisfied by the solution. It's natural because if we have singularity, then the solution at the singularity will go to plus infinity or minus infinity. So by no means it has the maximum principle. But if we consider the situation that there is no singularity, then indeed the solution will be bounded by the maximum and the minimum of its boundary data. Okay, the proof is simple. For example, if we consider minimum and the u is not constant, attains some minimum at an interior point x0, we can take the Laplacian u evaluated at s0, then it is non-negative. On the other hand, by the equation, we can evaluate it at s0. Since ux0 is the minimum, so both the first term and the second term are strictly negative. So here, give us a contradiction, okay? So if there is no singularity, u is bounded above and below by its boundary data. Okay, now I'm going to introduce our first result about the existence of uniqueness about the path with possible singularity. Of course, the first thing we want to figure out is what kind of singularity can the solution to the Poisson-Boltzmann model have. To answer this, we first consider a general elliptic equation Laplacian u equals g of u. And it has a possible singularity at some point in the domain. Okay. And for our case, Poisson-Boltzmann equation, g of u is nothing but c1 some constant times e to the u minus some constant c2 times e to the minus u. And for this equation, if n equals 2, the 2D case, Vasquez and Baron proved that if the growth rate of g is greater than the cubic growth, then the limit of the ratio of u to the log 1 over x exists, and the limit belongs to some range depending on the growth rate of g. Okay, if we put our Poisson-Boltzmann equation in, then ag plus and ag minus both equals 1 here, and the c is between -2 and +2. And as for n greater than 3 or equal to 3, Brazis and Baron proved that if the growth rate g is greater than s to the n over n minus 2, then all the singularity are removable. Of course, the exponential growth is greater than this algebraic growth. So we can combine these two results together to obtain some necessary condition for the possible singularity in the Poisson-Boltzmann model. That is, if n equals 2, the singularity of the solution U, either U can be smoothly extended across the singularity, that is, it's a removable one, or U has an order alpha j between -2 and +2 at Pj. The order means that the limit of the ratio U over log x minus Pj. Okay, and for high dimensional case, the Brodis-Véron result gives us that all the singularity are removable. So the next question is, this is a necessary condition. So if we have some prescribed singularity alpha j between -2 and +2, can the 2D Poisson-Boltzmann equation has a unique solution satisfy that U has such a singularity as the prescribed order? Okay, and the answer is yes. We prove that given any alpha 1 to alpha n between this range, then there exists a unique solution to the Poisson-Boltzmann equation. Okay, in addition, near each singularity Pj, we have a local decomposition of U. That is, U can be written as a singular part as a log function and a regular part Uj. And this Uj is a continuous function. And furthermore, we have some estimate of the gradient Uj of this form. And this estimate depends on the range of alpha j, but we can combine all these together. We can conclude that Uj is indeed an H1 function in this case. As for high dimensional case, n is greater than or equal to 3, because all the singularity are removable. So this is just the same as the case without fixed point charge. Okay, here's a remark. For two-dimensional case, though in the beginning we consider more general setting, that is, we don't just put the Dirac measure on the right-hand side of the equation, but just puncture the domain at some location of possible singularity. But eventually we can find that all the possible singularity is indeed the same of we just put the Dirac measure on the right-hand side. Okay, they are equivalent. Okay, so I'd like to give you some idea of the proof of existence and the uniqueness. As I mentioned earlier, that the Poisson-Boltzmann model has a variational structure. Say, we can write down the energy functional for this equation, and we can apply the direct method in calculus of variation to minimize this functional subject to all H1 function with trace U0, the boundary condition, and then we can obtain the solution of the Poisson-Boltzmann equation. Of course, this is indeed the case for n greater than or equal to 3, because for this case, there is no singularity. And the uniqueness is just follow the standard way to prove that when we consider two solutions, U1 and U2, we can take the difference and the difference of their equation to get some contradiction. Okay, so this is easy, but how about 2D case if there are some isolated singularity? Okay, so for 2D case, we use the ansatz that U equals B minus the summation alpha j log s minus Pj. Indeed, this singular part gives us our prescribed singularity. And then we can write down the corresponding equation satisfy V, and eventually we can find the equation of V also has some bilateral structure, and we can apply the direct method to find a solution of V. And then we can recover our original equation by V minus this guy. Okay. Then the next step, just standard to apply the ellipse theory to improve the regularity of our solution U or V. Okay. And for the local representation of U is similar to some study for Gaussian curvature equation studied by Cross and Rose. So I will not go through the detail here, but I just want to mention that the local representation of U is indeed crucial to prove the uniqueness of the solution. Because if we have two different solutions, U1 and U2, then we can write down their local representation near some PJ, and the difference of U1 and U2 in this case will become an H1 function, so that we can do integration by part or some manipulation without gaining some additional term from the singularity. Okay. Okay, so in the next, I'd like to talk about the asymptotic behavior of the solution. Before I introduce our results, I'd like to introduce some notation first. Okay, because we expect that the solution will approach some constant in the interior, but the solution will have boundary layer near the boundary, also near the singularity. It will be affected by the singularity. So we want to divide the domain into several parts to describe the solution in different regions. Okay, so near the singularity, we use a disk of radius sigma star to describe the solution near the singularity. As for the boundary layer, we consider the region omega eta denotes all the points in omega such that the distance to the boundary is less than eta. That is, omega eta is a strip domain, a strip space, a strip region near the boundary. Okay, and furthermore, we can choose eta star sufficient small such that on the strip, omega eta star will admit a normal coordinate. That is, all the points x in omega eta star can be represented by its distance to the boundary and its projection to the boundary. And this normal coordinate system, d and pi, the distance and the projection is indeed smooth on the region. Okay, so with this notation, we can describe our main results on the asymptotics. Okay, for 2D case, if U is a solution to this problem with singularity has order alpha j at each pj, then the first result tells us that for any compact subset K of the puncture domain omega with P1 to Pn excluded, then the difference of any 2 points will tend to 0 exponentially as epsilon tends to 0. Okay, this is a parallel result to the case without the isolated singularity. That is, the solution will become a very flat profile inside the puncture domain. And furthermore, we obtain a quantitative description of the solution U. That is, we get an approximation function capital U here with an exact error of order epsilon log 1 over epsilon, such that U can be written by some known function and the known coefficient. Okay, here in the interior, capital U is just a constant mu bar, and near the boundary, we use a function capital V0 epsilon to describe the boundary layer. And near the singularity, there are another function Vj epsilon here. Okay, So all the constant mu bar, Vj and the V0 are described by the boundary condition U0 and also the order of singularity. Okay. As for high dimension case n greater than or equal to 3, the result is similar, but just because that there is no singularity. So for the first result, the complex subset K is of the whole domain omega without singularity. And for the second result, the quantitative description, the function capital U can be defined only by using two regions, the interior and the boundary strip. Okay. Okay, in order to show you the asymptotics, the first step is to deal with the non-local coefficients under the denominator. Otherwise, if we deal with the equation with non-local coefficient directly, we cannot apply the usual, say maximum principle or covariance principle to this equation. So the first step, we find a transformation that we let capital M equals the product of these two integrals and take the square root, and the mu equals the quotient of these two integrals, take log and divide it by 2. Then if we define V equals U minus mu, then V will satisfy this equation. Okay, so we can see that in the equation of V, there is no non-local coefficient, although there are some constant M, mu, and epsilon. They are varying depending on epsilon. Okay, but if we take all these constants, we can at least apply some maximum principle and the covariance principle to the function V. Okay, so, and here's a remark that if the M is defined by the integrals of U, if we write it in terms of V, M will equals the integral of e to the v, and it also equals the integral of e to the minus v. Okay, so this equation of v doesn't have any non-local coefficient, but as I mentioned earlier, that there are 3 parameters depending on epsilon, and they will vary for different epsilon. So it will get some difficulty to analyze it. So our next step is to get some uniform bounds of m and mu, so that although there are m mu here, we can consider it is an order 1 coefficient, and also its boundary condition is bounded. Okay, so how to prove the uniform bounds of m and mu? For the lower bound of m, it can be directly proved by the Holder inequality, because its definition is the product of these 2 integrals with the square root. So Holder inequality gives us that it is greater than the measure of omega. As for the upper bound, we want to prove it by contradiction, that we assume that if there is a sequence m depend on u epsilon k will tend to infinity. And the idea is we want to find, okay, we recall that m equals the integral of e to the v. So the idea is we want to find a uniform bound of v independent of epsilon, so that e to the, so that the integral is finite, and it will give us a contradiction of the convergence to the infinity. Okay, so because the definition of m equals e to the b and e to the minus b, the integral. So without loss of generality, we can assume that mu of u epsilon k has a lower bound. Otherwise, if all the sequence of mu will tend to minus infinity, then we can just apply the same argument to minus b, because m equals the integral of e to the minus b. So that in that case, mu of minus u epsilon k will have a lower bound. So it's the same. So now with these two conditions, we can construct a function w of this form. That is, for the singular part, is nothing but the same as the positive singularity of v. So for those points, v tends to plus infinity. At least the w has the same order of v. And on the boundary, we can see that v equals u minus mu. That is, v has an upper bound because mu has a lower bound. So by choosing a constant w0 sufficient large, we can eventually find this w can be greater than or equal to v on the whole domain. And by our construction, this w gives us that the integral of e to w is finite. Okay, so we can get that m equals the integral of e to the v and is bounded by the integral of e to w and is finite. This gives us a contradiction. So we have the upper bound of n here. And as for the uniform bound of mu, it will follow the same idea to apply some covariance principle to get some control of mu. But the argument would be a little bit more complicated. So I will skip all the detail here. Okay, so now with the uniform bound of m and mu, we can start to have some properties of the solution of B. Okay, let's see the equation of B. The equation of B, we have some unknown coefficient m here, but if we combine m times epsilon square, then at least we know that it is of order epsilon square. And for the boundary condition, mu is unknown, but u0 minus mu is a bounded boundary condition. So we can apply some covariance principle to conclude that in any compact subset K in the puncture domain for 2D case or the domain omega for high dimensional case, V will exponentially decay to 0 as epsilon tends to 0. The idea is we apply the covariance principle to the equation of V squared. We can find that the epsilon square Laplacian V squared is greater than or equal to 4 over m times V squared. That is, V is some subsolution of this linear equation, and the exponential decay is straightforward. Okay, and this exponential decay in particular give us some control of V on the boundary of the disk near the singularity and the inner boundary of the boundary strip omega eta star. So we can use these two conditions to further obtain some approximation of V in these two regions, that is near the singularities and near the boundary. Okay, near the singularity, V can be approximated by some function capital Vj bar, and near the boundary, it can approximate it by some function capital V0 bar. Okay. Of course, because in the equation of V, there are coefficients m and mu are unknown. So the approximation function capital V J bar and the capital V 0 bar should be defined within the coefficient m and the mu here. Okay. So this is somehow good enough. That is, we already know that the solution have some rough behavior in the domain. But what exactly we want to get some exact description of the solution U in the domain. So we don't want the approximation still have some unknown coefficient depending on epsilon, though it's bounded. So let's see. In the definition of Vj bar and the V0 bar, here are m epsilon, and the mu epsilon here. So how can we replace these coefficients by some constant independent of epsilon? So the question we want to ask is, can we find some limits of m and the mu as epsilon goes to 0? Okay, so compared to our asymptotic behavior result, we want to show is m will indeed converge to the measure of omega, and the mu will converge to the constant mu bar. And if we can prove these two convergence with some error control, then we can replace the approximation function V bar to V with m and the mu replaced by omega major and the mu bar. Okay, so it's the last step that we want to show the convergence of m and the mu. For the convergence of m, we can start from the identities. M equals the integral of e to the b, and it also equals the integral of e to the minus b. Of course, these two integrals are equal, so we can rewrite m equals the average of these two integrals. And in order to get a measure of omega, here we can plus 2 and minus 2 in the integral. And the plus 2 will give us a measure of omega. And the remainder will be the integral of e to the b plus e to the minus b minus 2. So the next thing is to estimate this integral. Okay, the idea of the estimate is because we already have some approximation of the function small v by the capital V bar. Although capital V bar is defined by some unknown coefficient m and mu, but m and mu are both bounded, so it's enough to give us some control up to the order of epsilon. Okay, so we divide the domain omega into several parts near the singularities and the interior point and on the boundary. And in each region, we can use the approximation of the function small v, that is capital V bar, to calculate the error estimate. Okay, so near the singularity, we have an epsilon square order. And in the interior point, we have exponential decay. And near the boundary is epsilon order. So we combine all this together, we have the convergence of m and to the measure of omega is an epsilon order error. Oops. Okay. Also, we want to prove the convergence of mu to show that the coefficient mu will converge to mu bar. We also start from this identity, but we take the difference. We have the integral of e to the b minus e to the minus b is 0. And for this integral, again, we follow the same idea to divide the domain omega into several parts near the singularity, interior point, and near the boundary. But here, near the boundary, on the boundary strip omega eta star, we need to further decompose it into two parts, one with a width of order epsilon log 1 over epsilon, and the remainder. Okay, so if we play the same trick that we use the approximation functions of D to the first integral, it gives us an epsilon square order. And again, in the interior region, it has exponential decay. Okay, as for near the boundary, the third integral, indeed, if we can choose the constant n star sufficient large, we can have a higher order of epsilon here. So what we want to do is a lesser integral. For the lesser integral, of course, for the approximation of the small b, we will have the difference, which is of order epsilon square log 1 over epsilon. On the other hand, if we just take the approximation function in this integral, we will have epsilon times some bounded coefficient times this integral, and with some epsilon square error term. So we can combine all this together to conclude that, okay, this is epsilon square, this is exponential decay, this is high order of epsilon, this is epsilon square. They are all higher order of epsilon. And this is epsilon square log 1 over epsilon. This is epsilon times this integral. So we have this integral is order of epsilon log 1 over epsilon. And we can solve mu epsilon in terms of integrals of e to the u0 over 2 and e to the minus u0 over 2. And conclude that the convergence of u to mu bar has the error estimate epsilon log 1 over epsilon. Okay, let's remark here. If we don't further decompose the region near the boundary into two parts, that is, we just put the integral over omega eta star here, then the difference will give us just order epsilon instead of this one. And the next integral still give us epsilon times this integral. So the result will become this integral is order 1. We just get the boundedness, but not the convergence. So this decomposition is crucial to obtain this convergence. Okay, so my talk will just stop here. Thank you very much.